All right, so we're ready to actually go through and do some hypothesis testing. Our first example, we have a sample of data where the sample mean is 20. We use 32 data points. Our standard deviation, our population standard deviation is 4, and then we're going to do a hypothesis test where we're testing whether the mu is 22 or less than 22. So this is going to be a left-tailed hypothesis test, and we're going to use 5% significance. Okay, so that's going to be our alpha. Our alpha is 0.05. So we're going to have two ways to do this. We're going to have, again, what I'll call the critical value way, the critical value approach, or we can do the p-value approach. Okay, so the p-value approach. Yeah, we'll go through each of these. So first we'll do the critical value approach. So our idea is we're going to take all of our data and compute the standardized variable. That's going to be our x bar minus mu naught divided by sigma over square root of n. So that's going to be 20 minus 22. Our mu naught is the value that we're always testing in the null hypothesis. So 20 minus 22 over sigma divided by, oops, that should be a 4, divided by 4 divided by square root of n, and our n is 32. And when we type this in, what we get, I'm just going to use r as a calculator, is we get that z naught is negative 2.82. I guess let's go to 3 decimal places here, not for any good reason, but negative 2.828. Okay, actually, let me go to just 2 decimal places, because our standard normal table in our student t-distribution table only go to so many decimal places. Doesn't really matter how many we go to, but this is enough for me. R, let me take a step back here. R is actually going to, my math lab is going to actually want us to be more specific. So since we have it, let's just go to 4 decimal places. Say negative 2.8 to negative 2.8284. Okay, there we go. It's not really going to change our decision. I just want to be consistent with what we're going to be expected to do on tests and so on. So this is our critical value. If we have a 5% significance level, what we're going to do is we're going to look at our standard normal distribution. We have to think about what's our cutoff. So this is going to be negative z sub 0.05, and that z sub 0.05 value is going to be found on our t-distribution chart. So if you remember, this is a value in the standard normal distribution, and on the handout that I gave you in class, on the front we had the standard normal distribution, on the back we had the student's t-distribution, but underneath the student's t-distribution, just that's where it naturally, that's where it actually fit, like physically fit, had the room for it on the sheet, was on the back. So even though it's on the t-distribution side, it's really a normal distribution measure. It's really a quantity referring to the normal distribution. So if we look at that and we look at the cutoff z sub 0.05, it turns out that this value is going to be negative 1.645. Okay, so that's our critical values, negative 1.645. Negative 2.8 lies to the extreme of that, right? It lies to the left of that. So our negative 2.8284 value lies to the left of that. In other words, it's in the rejection region. Okay, so that means that we're going to reject. Okay, so we reject the null hypothesis. Okay, there is enough data to say that mu is less than 22 at the 5% significance level. Okay, that's how that works. That's the critical value approach. The p-value approach is very simply just compute the p-value. And this is a left-tailed test. That means that all we have to do to get the p-value is we're going to plug in to r p-norm of negative 2.8284. right? Be as precise as you want. The fact that you have the actual value in R means you can just copy and paste it, but let's just look at p norm, negative 2.8284. And it turns out that our p-value is going to be 0.0023. Okay, p-values I'll just take to 4 decimal places. And the p-value approach is going to say that since p is less than or equal to alpha, we're going to reject the null hypothesis. Okay, we of course get the same conclusion. Either way we want to do this, right? The critical value approach or the p-value approach. But that's the idea. So since our p-value is less than or equal to alpha, we reject the null hypothesis. Okay, that's the idea. So next, we're going to use, it looks like we have a two-tailed or two-sided hypothesis test, just based on the alternative hypothesis. Our significance level is going to be the same 5%, and what we're going to do is we're going to, again, do the critical value approach, or later we'll go back and we'll do the p-value approach. Our critical value approach is we're going to compute our test statistic, z naught, so that's going to be our sample mean minus mu naught over sigma divided by square root of n. And if we plug all that into R, what we're going to get is, we're going to get that this is 3.1623. Okay, just to go to 4 decimal places, like I said we would up here. Okay, so 4 decimal places, that's our standardized value, 3.1623. And so, again, the critical value approach is at the 5% significance level. We need to decide what are our critical values. This is a two-sided test, so we need to decide what are the critical values where each area over here is 0.025. So our critical values will be plus 0.025 and minus 0.025. Okay, those are the z sub 0.025, I mean. And so if we go back to our chart and look up those values, the z sub 0.025 values are 1.96 and negative 1.96. And so what that's going to mean is we're going to reject the null hypothesis because our value is in the rejection region. It's more extreme, right? 3.1623. It's more extreme than our data. This is the rejection region. And so we'll reject the null hypothesis. Okay, it turns out we do have enough data to say that the mean is not equal to 11. Okay. That's how that'll work. Finally, with the p-value approach, for the p-value approach, what we're going to do for the p-value approach is we're going to say, let's see, we're going to look at our p-value approach and we're going to have to compute our p-value. So we're going to get p is 2 times p norm of minus 3.1623. And if we plug that into R, we're going to get something really tiny. I know it's going to be really tiny because since this is the standard normal distribution, having the value 3 means that we're at least 3 points, at least 3 standard deviations away from the mean. And so our value is going to be tiny. So it's going to be something like, it's going to be less than 0.3% or 0.003. We'll figure out exactly what it is here in a second. So if we type it in, we're going to get 2 times p norm minus 3.1623, and lo and behold, it's 0.0015. So this is, even after it's multiplied by 2, it's 0.0015. Okay, so 0.0015. Actually, if I'm rounding correctly, I think my math lab would yell at me for that, but it's 0.0016 because it's 0.001565, blah, blah, blah. So 0.0016. P is definitely less than or equal to alpha. So So we reject the null hypothesis. Okay. That's the idea. That's our conclusion. We'll do the next